Swayam Prabha. Digital India. Educated India.
Now, go back and let us take a step back and see where we are. We have a set C which is a closed convex cone, and now we have a point 1 comma 0 that lies outside C, okay, and C is a closed convex cone. So, C is a closed convex cone, 1 comma 0 lies outside C. What does this mean? That it means there exists a separating hyperplane that separates 1 comma 0 from C, right. So, this point can be separated from C, okay. So, which means there exists a separating hyperplane. Now, the separating hyperplane, remember C is a set in R m plus 1. So, the hyperplane should also have its normal should also have m plus 1 coordinate. Okay. So, let me write it like this. So, there exists a s comma y not equal to 0. Okay. So, this is the hyperplane normal. Such that s comma y transpose 1 comma 0 is less than the infimum of s comma y transpose r comma w, where r comma w belong to the set C. Let me write this more a little neatly. So, s comma y transpose 1 comma 0, right, this is less than the infimum of s comma y transpose r comma w for as r comma w ranges in C. Now, let us just evaluate this. S comma y transpose 1 comma 0 is simply S, that is my left hand side. Right hand side is infimum of S into R, because they are both scalars, plus y transpose W. These are both vectors of length y, right, as R comma W belongs to C. So, now S must be less than this, and we know that S comma y as a vector as a whole is not equal to 0. That means, it cannot be that all its components are 0, all right. Okay. All right. So, now tell me, what can you say about this thing, the green thing that I have just underlined? The infimum of S r plus y transpose W as r comma W ranges over C. Remember, C is a closed convex cone, right. So, if r comma W is in C, then a scaled version of it is positively scaled version of it is also in C. So, what should be the value of this infimum? This infimum is minimized. What you are doing is effectively minimizing a linear function over a cone, right. A linear function, the slope of that linear function is given by S and Y, and the point in the cone is r comma W. R comma W ranges in this cone. So, what can you say about this, the infimum here? So, let's suppose it can it be a positive value? Can it be 5, 3, 1.5? If it is any positive value, right, then because C is a cone, I can always scale it down and bring it down to 0. right. I can all, if some r comma w gives me a value 5, suppose, I can take 1/10 of r comma w and get a value of 0.5, right, 5 by 10, right. Essentially, I can bring the value down as much as I want and eventually bring it to 0. So, the infimum cannot be any some positive value like this. Can it be a negative value? So, this infimum cannot be positive since C is a cone. Can it be negative? Can it be -1? Why? Again, you can scale it in the opposite direction. You can magnify also, right. So, if it is -1, I can multiply it. If an r comma w gives me a value -1, right, I can take twice that and get -2, 10 times that and get -10, and so on, and I will not lose feasibility at all. So, I will remain in the cone, right. So, I can scale up and then go down to -infinity. Now, what is the problem with -infinity? I know that this infimum is definitely greater than some s, where s is some finite value. We have been guaranteed that there exists such an s, right. It is some finite value. I do not know what it is, positive, negative, whatever. It is definitely some finite value, right. So, if it is, so the infimum therefore cannot be -infinity. So, it can't be positive. So, infimum, if it is positive, then you have a contradiction, you can bring it down to 0. It cannot, positive value cannot be an infimum. If it is negative, then it had to become -infinity. That is also not possible because of this inequality. So, in other words, we are left with just one choice. What is the infimum then? The infimum must be 0, right. So, let me summarize this. So, cannot be negative, again, since C is a cone. Cone, and C is a cone and S is finite. Make the value so, in other words, the optimal value has to be 0, right. So, consequently, what we have is that S therefore is strictly less than 0. Okay. And the optimal value, let us call this here, let us call this optimal value say C star. C star is equal to 0. Okay. Now, the optimal value is 0 and S is strictly less than 0. This is what we have concluded so far. Now, since the optimal value is 0, what this means is, let me go to the new page. So, C star is equal to 0, which means basically infimum of S r plus y transpose w as r comma w ranges in C. Okay. This, the infimum here is equal to 0. Okay. And we have that S is strictly less than 0. Now, S r plus y transpose w is the infimum of that is equal to 0, which means S r plus y transpose w is greater than equal to 0 for all r comma w belonging to C. Now, r comma w belongs to C, then go back to the definition of the set C. We define the set C here. This is how we define the set C. R is T z 0 minus C transpose x, and W is T b minus A x for some x greater than equal to 0 and t greater than equal to 0, right. So, let me substitute that. This is greater than equal to, so I have S r plus y transpose W greater than equal to 0. I just substitute this, I get S times T z 0 minus C transpose x plus y transpose T b minus A x greater than equal to 0 for all x greater than equal to 0 and t greater than equal to 0. Let me rearrange this a little bit. So, I have just rearranged a few terms here. I picked up the terms that a couple of terms that involve x and put them together here. So, this is C transpose x, there is a minus s which I pulled out outside. I took y transpose a x. Okay, there is a minus minus sign here, that minus sign has come here, and since I pulled a minus s outside, that I have divided by a minus s. Right, just I am writing this specifically in this kind of little non-intuitive form for a particular reason, and then everything else I have put here. So, I have a y transpose b that was multiplied by t. So, t has come out, and I have an s t z 0 which is left here. Right. So, all of this is greater than equal to 0, and remember this has to be true for all x greater than equal to 0 and t greater than equal to 0. Now, this claim here, this inequality has to be greater than equal to 0 for all x greater than equal to 0 and t greater than equal to 0, right, which means I can put my favorite values of x and t and check, right. Say first, so I can put, say first, let us suppose we put say t equal to 0. What if I put t equal to 0, what do I get? If I put t, so put t equal to 0 here, then this term disappears. The second term here disappears because it's been multiplied by t. So, all I am left with is then minus s, C transpose x minus y by minus s transpose a x greater than equal to 0 for all x greater than equal to 0. Now, remember s was negative, s was strictly negative, we just concluded that. So, I can just divide throughout by minus s is a positive quantity. So, I can just cancel this minus s out, and what I am left with then is C transpose x minus y by minus s transpose a x greater than equal to 0, and this is true for all x greater than equal to 0. Okay. So, let me again gather the x terms together. So, this is saying so, this has to be greater than equal to 0 for. So, what I have got is C transpose C minus A transpose y by minus s, the whole thing transpose x greater than equal to 0 for all x greater than equal to 0, right. Now, this has to be greater than equal to 0 for all x greater than equal to 0. What does this mean? So, it is I am taking an inner product of some vector with x, and I want that inner product to be greater than equal to 0 whenever x is greater than equal to 0. So, what sort of components should that inner product that vector have? Non-negative components, right, because if any of the components is negative, then what I can do is make my x very large for that component and 0 for everything else, and that will give me a negative number. That will not give me a greater than equal to 0. Right. So, the only way this is possible is that the term in the bracket is less than equal to 0. So, A transpose this is less than equal to C. Okay. So, let me just box this. This is my first conclusion. A transpose y by minus s is less than equal to C. All right. Look, we got to this by putting t equal to 0. Let's now put x equal to 0. Suppose I put x equal to 0, what do I get? So, now this term, the first term here is going to disappear. If I put x equal to 0, if the if I put x equals 0, this all these terms are going to all be 0. So, all I am left with is the second term, which means I have t times s z 0 plus y transpose b greater than equal to 0 for all x greater than equal to 0 and t greater than equal to 0. All right. Okay. So, now let me once again do the same thing that I did earlier. I know that minus s is positive. So, s is negative. So, minus s is positive. So, let me write it like this. Let me write this whole thing in the following way. So, since I have put x equal to 0, I do not need the x greater than equal to 0 here. I just need this to be true for all t greater than equal to 0. Now, okay, in fact, we can do a quick analysis here also. Since this has to be true for every t greater than equal to 0, it just means, what does this mean? T is greater than equal to 0. This has to be true for every t greater than equal to say t equal to 100. This must be true for t equal to 100. So, what does this mean? Yeah, so it means that the term that is in the bracket must also be positive, right? Must also be non-negative, which means S z 0 plus y transpose b is also greater than equal to 0. Okay. So, let me rewrite the whole thing. Rewriting it basically gives me b transpose y by minus s is now greater than equal to z 0. I can divide throughout by minus s, and the inequality does not flip sign, because minus s is positive. Right. So, I got b transpose y by minus s is greater than equal to z 0. Right. So, here is my second conclusion. So, now what do these two box conclusions mean? The first conclusion here says that y by minus s satisfies A transpose y by minus s less than equal to c, which means y by minus s is feasible for my dual. Y by minus s is a feasible point for the dual, right? And the second one says that the optimal value, the value of y by minus s, the objective value is greater than equal to z 0. And what was z 0? Z 0 was the optimal value of the primal. So, which means I have found a feasible point for the dual. Okay. So, y by minus s is feasible for the dual and satisfies B transpose y by minus s greater than equal to optimal value of primal. But then what did we know from weak duality? Weak duality told us that this inequality is actually the opposite direction, right. So, weak duality told us that B transpose y has to be less than equal to the optimal value of the primal for every feasible y. So, now we have found a feasible point y by minus s such that its value is greater than equal to the optimal value of the primal. So, which means the only way this is possible is that there is equality throughout, right, which means that now by weak duality it is the optimal value of the primal. And in fact, this automatically shows that y by minus s must be the optimal value, must be the optimal solution of the dual also, right. So, which means in fact that the optimal value of the dual is equal to the optimal value of the prime. So, it has shown that the optimal value is attained by y by minus s. That is the point that attains it. We know that it exists. We know that we also know that the optimal value of it is must be equal to that of the primal. Right. So, weak duality gave us the inequality in one direction, the other inequality came by through this theorem basic, and what was the key idea we used in it? Separating hyperplanes, right. The existence of a separating hyperplane. We basically constructed a set C and strategically chose a point outside it and showed that you can separate the two. Using the fact that they can be separated, we got our result. Now, you might wonder obviously how did someone think of this particular set, how did you think of that particular point, etc. That we will build the intuition for that later in this course or in the following lectures also. The basic intuition for it is to remember that this set C is actually nothing but the projection of this set S, the set S that I have shown here. And what does this set S have? The set S has a representation here of the feasible points for the primal as well as the feasible points for the dual. You can say for effectively it has a x which captures the feasible point of the primal, and it has a w which captures a variable for the constraints, one for each constraints. And how many variables are there in the dual? You go back and see the variables there are as many variables in the dual as there are constraints in the primal. Every constraint in the primal gets one dual variable, and every constraint you can say in the dual gets one primal variable, right. So, this is obviously reminding you of something that you have already seen, which is that the dual must have some relation with Lagrange multipliers. You have seen Lagrange multipliers as variables that you have one per constraint, right. And effectively that is what that is what we are seeing here. So, in fact, the optimal value of y is actually the optimal value of Lagrange multipliers for this particular problem. Now, I have not taught you Lagrange multipliers as yet for inequality constraints and so on. So, we will come to that, but that will become evident very quickly. But essentially, the main reason why this the thinking behind this is to capture the problem in both the space of the primal as well as the dual, means both in the space of the decision variables as well as in the space of the constraints. And that is there are many different ways in which such sets can be constructed, and they all lead you to duality type theorems like this. Okay. So, the correct tension that's present in an optimization problem is always the tension between not multiple decisions that you have to make, but rather the decision between the tension between the decision variables and the constraints, and or essentially the Lagrange multipliers, and that is being captured by this particular set. So, you will see more of this as we go later in this course. Okay. So, to summarize, essentially what we have shown is that the first thing, which is weak duality, that is a claim that holds for free, or I mean almost for free. It just comes by the way this is constructed. You can immediately argue that. And but moreover, there is also this claim that if a primal has an optimal solution, then so does the dual, and the optimal values are equal. Now, this also means this also has computational implications. For example, it may be that primal looks much harder to solve than the dual. Does not matter, you can solve either and you will get the same answer, right. So, it has that is one of the motivations behind algorithms also. Okay. I will in the next class I will give you another application of strong duality, okay, that arises in network flow problems. Okay. So, we will end here.